Hey everybody, here's a video on division of complex numbers. And so the two complex numbers, one concept that'll be important in division is conjugates, right? We talked about conjugates before. So remember, it's when you have a binomial and you keep the same two terms, but you change one sign, right? So instead of a plus bi here, we have a minus bi, right? Those are complex conjugates of each other, right? So just like conjugates we've seen before, except now we're dealing with complex numbers, right? Because they have a real component and an imaginary component. Now, if you remember, the cool thing about conjugates is if you multiply them together, a plus b times a minus b, remember what you get is a squared minus b squared, correct? So now what we're doing is we're throwing an I into the mix, right? So it's a plus bi times a minus bi. So it's still going to be a squared, and it's still going to be b squared, but um, we're also going to square I, right? Because we're going to get the first term squared minus the second term squared. So if I square bi, the quantity of bi, I get b squared I squared, okay? And we all know that I squared equals, that's right, -1. So if I multiply -1 times positive b squared, then what I get is, or excuse me, if I multiply -1 times negative b squared, then what I get is positive b squared. All right? Okay, so negative b squared times -1, that's how we get positive b squared, right? So the product of um, the two complex conjugates is always a squared plus b squared, okay? So let's check out an example. So this says find the product of a given complex number and its conjugate. I don't know why that number got cut off there, but anyway. So what I'm going to do is I'm going to multiply 3 plus 5i times its conjugate, 3 minus 5i. So then I can distribute, and so what I get is 3 times 3, well, excuse me, 3 squared, right? Doing the shortcut here. 3 squared is 9 minus, or excuse me, in when we have complex conjugates, it's going to be plus, and then I'm just going to do b squared, right, which is 5 squared. So it's 9 plus 25. So notice I don't have an I in the result, right? And the reason why it goes back to the last slide, what happens is the I gets squared and it turns that second term from negative to positive, right? And so 9 plus 25 is, all right, and that's our final answer. Okay, now remember, you could FOIL this all the way out like I actually wrote initially, but yeah, you can definitely use a shortcut. If you did FOIL it out, you would get 9, right? And you would get negative 15i, and you would get positive 15i, and those would cancel out. And then you would get 5i times negative 5i, which is negative 25i squared. And once again, the I squared would turn to -1, and so it would, turn that negative 25 into a positive 25. Okay, and so these would cancel out, and you get 9 plus 25, which is 34. So you can always do that, but you're also welcome to use the shortcut. Okay, so the second one, we have 3 minus 2i, and so I'm going to multiply by its conjugate, which is 3 plus 2i. At least one of its conjugates, right? There's two conjugates. But it's usually better to change the middle sign instead of changing the first sign, right? So I could also make a conjugate that was -3 minus 2i. But then instead of getting a squared plus b squared, you would get negative a squared minus b squared. All right. So usually it's beneficial to change the middle sign. All right. So that's what we'll pretty much do all the time on the board and on the notes here. So I'm going to get a squared. So that's going to be 3 squared, which is 9. Then I'm going to get b squared. Remember, b, not the I, just the b squared. So it's going to be 9 squared plus, 3 squared plus 2 squared, which is 9 plus 4, which is 13. Simple as that, right? Now, the cool thing about multiplying conjugates is we just went from a complex number and we multiply by its conjugate, we get a real number, right? Same thing over here. We went from a complex number to a real number, okay? So we go from multiplying two complex numbers that are conjugates, and then we get a real number, right? A squared plus b squared. There's no I involved. There's just the real numbers squared and added, and so that's the benefit of multiplying by conjugates. So how does that help us with dividing complex numbers? Well, if we're dividing two complex numbers, like here, the issue with that is, well, for one, we want to try to simplify it. For two, we want to rationalize, or in this case, realize our denominator, right? We have an imaginary number there. So how do we make that into a not only real but rational, right? So what we can do is we can multiply by the conjugate, right? And if we do that to the bottom, we do the same thing on top. And so what will happen is on the bottom, we'll end up with the real value, c squared plus d squared in this case. And then on top, we'll just have to do the work, okay? So that's kind of what's going to happen when we divide complex numbers, is we're going to multiply by the conjugate of the denominator on top and bottom. And that'll help us to not only rationalize the denominator, but realize the denominator. So here are some examples. The first one, we have 3 divided by 2 minus 5i. So what I'm going to do is multiply by the conjugate of the denominator in order to make it real, right, and rational. Okay, so we're going to, on the bottom, we can use the shortcut, and we can get 2 squared plus 5 squared. Okay, then on top, we can distribute, so we get 6 plus 15i. And so we'll simplify here on the bottom. It would be 29. Then on top, 6 plus 15i. Cool. So that would be it, right? And sometimes that would be a fine answer, and that's definitely equivalent. But it says write your answer in the form of a plus bi, right? So what I want to do is I want to split this up into an imaginary and a real component. So I'm going to say 6 over 29 plus 15i over 29, and I'm going to write it like this, 15 over 29i. Okay, so then we have our real component a, right, plus our imaginary component bi, right? So we can clearly see that b is 15 over 29, a is 6 over 29, right? And we have the I tagged along. So this is one of the main benefits to rationalizing or realizing the denominators. You can keep the components separate, right? Which is really important when you're dealing with complex numbers. All right. So this next one, we have 3 minus I on the bottom, right? 2 plus I over 3 minus I. So the top is fine, but I want to make sure I realize the denominator, so I'm going to multiply by its conjugate, okay, which is 3 plus I. Okay, so on the bottom, I'm going to do the shortcut. I'm going to do 3 squared, which is 9, plus, what's the coefficient of I? You guessed it, it's a 1, right? So I have an invisible 1 there, so it's going to be 3 squared plus 1 squared, and 1 squared is 1. On top, we're going to have to do some FOIL, or distributing. So we're going to get 2 times 3 is 6, 2 times 1 is 2i, I times 3 is 3i, and I times I is I squared. And I squared equals -1. Okay? So when I simplify on the bottom, 9 plus 1 is 10. On the top, I have 6 and 6 minus 1, which is 5. And then I have 2i and 3i, and that makes 5i. Okay, so I want to separate these to make it into, or to convert it to standard form for a complex number. Oops. Let me go back a second. So I'm going to split up 5 over 10, the real component, plus 5i over 10, which is the imaginary component. And then I can reduce. So I get 1 over 2 here. So 1/2 plus 1/2 I, right? And you could also put I over 2, that's fine with me. But just to kind of clearly show A and B, I'll write it like that. All right. And then last but not least, how do we do C? So if, pause for a second and see, what would you think? What would you do to get that denominator real? All right, so if you said we should multiply by I, you're correct, right? So this is a monomial on the bottom, so we don't have, we can't multiply by its conjugate. I guess we could, if we thought of it as 0 plus I, and then we could do 0 minus I. But we don't. We can just multiply by I on top and bottom, right? We could also do negative I to kind of cancel out the negative, but we'll just multiply by I and see what happens. So I times I is I squared, right? We'll do that, leave it there for a second. And then on top, I'm going to distribute. And so 5 times I is 5i, and then -4 times I is -4i squared. Okay, so now we have these I squared terms, and we know that I squared equals -1. So we have 5i, and then we have -4 times -1, which is +4 all over -1, right? So remember, we want to separate these, and you always never, you never want to leave a -1 at the bottom. That can always be simplified, right? Basically, when you divide everything by -1, it changes the signs, right? So what's going to happen is I'm going to have 5i divided by -1, which is -5i, and I'm going to put that in the back. And then I'm going to have 4 divided by -1, which is -4. Okay, so there's our complex answer, and it's in standard form, right? -4 minus 5i. One thing I want to mention here is, so what happens here is, just like when we were multiplying complex numbers, we get a complex number. Same thing when we're dividing, right? We're dividing two complex numbers, and we end up with a complex number result, right? So every time you operate with complex numbers, you result in a complex number. And that's kind of a unique property or quality of complex numbers, because if this were a variable like x, it wouldn't work out this way, right? There would be no way to get rid of the x in the denominator and so forth. So, so that's one of the unique things about complex numbers and why they're used in the real world, in electrical engineering and current and things like that.